Welcome back to the deep dive. Most of us, we interact with crypto through these really slick, simple mobile apps. But what's actually going on when you tap send?
Yeah, what happens behind the screen?
Exactly. So today, we're going deep, like forensic analysis deep into a Pi Network transaction.
Uh-huh. Our mission really is to crack open that raw data. You've got complex JSON, encoded XDR. We want to answer. What specific bits of information are actually being permanently etched onto the blockchain?
And, maybe more importantly, why should you care about those specific bits? Quick refresher for anyone new. Pi Network, started by Stanford PhDs, launched back in 2019.
Right. And the goal is, mass crypto adoption using this super simple, eco-friendly mobile mining idea.
Which is basically open the app, hit a button once a day. Simple as that. But like you said, that simplicity, it hides some pretty sophisticated stuff underneath.
It really does. And the data we're looking at today, it's fundamental. It underpins the whole system's immutability, its transparency. We've waded through the transaction dumps, the tricky parts so you don't have to.
Bringing out the key takeaways.
Exactly. The critical nuggets, the stuff that defines how it works, and crucially, where the real risks might be hiding.
Okay, let's start unpacking this. The basic transaction skeleton first. When a transfer actually happens, there's this high-level JSON structure, right? It gives us the immediate status.
Yeah, that structure is, well, it's vital for quick confirmation. Every single transaction gets a unique transaction ID and a really clear, successful status, just true or false, plus a precise timestamp. We're talking down to the second, like 2025-03-29T 16.05.18Z. Gives you that immediate, verifiable proof of when it happened.
Got it. Now let's talk about who's involved, the participants. Because this is where Pi Network uses some, well, clever tricks inherited from Stellar, its base platform, to be more efficient.
Right.
You've got the sender, the source account, that looks like a standard Stellar address, starts with a G. Seems pretty straightforward.
It is, but then the destination account, the receiver, that's often a bit more complex. This is where you'll often see what's called a muxed address.
Muxed address.
Okay.
And it's not just, a random string. It's a deliberate technical choice, aimed at scaling, really.
How so?
Well, the muxed address, it combines the standard G parent address with a second piece, a sub-account identifier. Often you see it marked with an asterisk, like 8.
So why bother with this two-part address? I mean, for a network pushing simplicity, doesn't that feel a bit complicated?
It feels that way, but the complexity actually serves efficiency. See, that sub-account part in the muxed address, often it actually doubles as the transaction memo itself.
Ah, okay.
So by packing the who, the parent address, and the what for, the memo or sub-identifier, into a single field, they save valuable space and processing steps right there on the blockchain.
Right, less data to store and verify.
Exactly. And if you're aiming for, billions of users, massive throughput, these tiny savings, they really start to add up.
Okay, that makes a lot more sense now. It's a technical shortcut designed for scale. All right, before we dive deeper into that memo, let's talk about the money itself, the actual value transfer.
Yeah. We see the amount, maybe it's, say, under 99.99 pi.
Huh?
And the network takes its standard fee, which is, what, 0.01 pi?
That's right, 0.01 pi, fixed fee. And the asset is just confirmed as native, meaning it's the actual pi token being moved.
Okay.
And here's our first really critical nugget for you, the listener. That nice, clean number you see, 199.909. That's just for display.
Uh-oh. Why?
Because blockchains, fundamentally, they have trouble with floating point math, decimals. It can lead to inconsistencies.
So what's the real unit, the one that's actually stored immutably on the chain?
It's the Stroop. Pi Network, like Stellar, uses this incredibly small subunit. Think of it like cents to a dollar, but much, much smaller.
How small?
1 pi equals 10 million Stroops. That's 10 to the power of 7.
10 million Stroops per pi.
Yeah. So when you send 199.99 pi, what's actually recorded on the blockchain is 1,999,900,000 Stroops. All whole numbers.
And the fee, that 0.01 pi.
That's exactly 100,000 Stroops. Again, a whole number. This precision, using Stroops, lets the network handle tiny fees reliably and totally avoids any rounding errors when transactions are bouncing around the globe.
Okay, so it's the classic difference between what's easy for humans to read and what the machine needs for absolute truth. Got it. Now, let's shift to what you flagged earlier. Maybe the single most dangerous part of a transaction if you mess it up. the memo system.
Dangerous is the right word, especially when dealing with centralized exchanges or CEXs. This memo field, it's the bridge. And if you're sending Pi to a CEX, it is absolutely non-negotiable.
Why is it so critical for exchanges?
Because the memo acts as your specific identifier on their system. It could be text, a number, some kind of code they give you. Its only job in that context is to tell the exchange, this incoming Pi deposit, it belongs to this specific user account.
And here it is, the big warning label. The trapdoor, as I called it earlier.
Exactly. If you, listening right now, forget to put that required user deposit ID into the memo field when you send Pi to, say, gate.io or another CEX, poof, those funds arrive at the exchange's main wallet, but they have absolutely no way to link that specific transaction back to your account. It gets lost in their massive pool.
So the Pi is just
Yeah.
gone from your perspective.
Essentially, yes. Lost forever in the exchange system because you didn't provide the key, the memo, to unlock it for your account. You miss the memo, you lose the Pi. It is that simple and unfortunately that harsh.
Wow. Okay. Message received. Double, triple check that memo for CEX deposits.
Cannot stress it enough. That little field dictates who owns the funds once they hit the exchange's walls. But it's not just for exchanges. The memo system, Pi Network uses it heavily internally too.
Oh, really?
Yeah.
How is the Pi Core team using memos for their own stuff?
While they use it for really essential identity management and tracking, the memo helps link a user's blockchain wallet address back to their specific account within the Pi mobile app.
For KYC and things like that.
Precisely. It's critical for verifying ownership during the KYC process and also for managing the migration of users from the old testnet days over to the current mainnet beta. We see specific memo formats used for this, like an example might be MBP-BVO-YNCQ for HHTCN967U-AR14.
Okay, and that MBP prefix. Yeah. Does that give us a clue?
We think so. It very likely stands for mainnet beta participant.
Makes sense.
And the rest of that string, it's just a unique random code, a hash used specifically for that vital pairing. Linking the on-chain identity to the off-chain user account for the core team's tracking and compliance needs. It's a clear technical choice supporting their KYC framework.
Right. Okay, so we've covered the JSON basics, participants, stroops, and the critical memo. Now let's peel back another layer. We're moving from the human-friendly JSON wrapper to the raw, unchangeable core data itself, the XDR.
Exactly. Think of the JSON as the pretty cover on the book, the XDR. That's the actual text, the unalterable source code of the transaction.
XDR, that stands for External Data Representation.
It does. It's a standard way to encode data structures so that any machine anywhere can read it exactly the same way. Doesn't matter if it's a Mac, a PC, a server. The data is interpreted identically. That's why it's so crucial for distributed systems like blockchains, especially Stellar-based ones like Pi Network, ensures all the nodes agree.
Okay, so what key information is actually packed inside that dense XDR code?
We mainly look at two big pieces. First, there's the envelope hexadecimer. This holds the complete raw transaction details. We're talking the full exact participant addresses, including MUX details, the precise amount in stroops, the memo field, critical, and also time limits for when the transaction is valid. It's the full set of instructions for the network.
The instruction set. And the second piece, does that record what actually happened?
That's the result metaxdr. So once the network tries to execute the instructions from the envelope, the result metaxdr records everything that happened after. It tracks the exact changes to account balances, notes the fees that were paid, and lists out the sequence of operations that were actually performed successfully. Think of it as the official audit trail of the execution.
This level of detail, this immutability, it leads us right into our third segment, security and trust. We've got this permanent record. But how does the network guarantee that I, the sender, genuinely authorized that transaction? And how do we know nobody tweaked that XDR envelope while it was flying across the internet?
Great questions. This is where public key cryptography comes into play, specifically through the digital signature. That signature provides two absolute guarantees: authenticity and integrity.
Okay, walk us through how that signature gets created.
Sure. So first, you take the entire transaction data, everything inside that XDR envelope, and run it through a hashing algorithm, like SAJ256. This creates a unique, fixed-length digital fingerprint of the transaction. That's the transaction hash.
Like a unique ID based on the content.
Exactly. Now, that hash is the target. To sign the transaction, the sender uses their private key, the secret key only they possess, to encrypt that transaction hash.
Okay.
The result of that encryption, that's the digital signature, and it gets attached to the transaction envelope before it's broadcast.
So the signature itself proves it could only have come from the owner of that private key.
Hmm.
That's authenticity. How does the network verify it? And check for tampering, the integrity part?
Verification is the magic part, and it uses the sender's public key, which everyone knows. Anyone on the network can take the signature, and using the sender's public key, they try to decrypt it.
Okay.
If the result of that decryption perfectly matches the transaction hash, which the verifier can also calculate themselves directly from the transaction data, then two things are proven simultaneously.
Pranathi.
One, it must have been signed by the owner of the corresponding private key, authenticity. Two, if even one tiny bit of the transaction data had been changed after signing, the hashes wouldn't match, so the decryption would fail, integrity. It guarantees non-repudiation. You simply can't deny you sent it if the signature is valid.
That's a much clearer picture than just saying, oh, it's signed. Okay, we've really hammered home the biggest reason for failure, that missing memo for CEXs. But what other, maybe more technical issues can cause a transaction to fail, even if it's perfectly signed?
Yeah. Beyond the memo, there are a couple of main areas that depend on getting the details right. First is the fee structure. If the transaction specifies a maximum fee it's willing to pay, but that's lower than the current minimum fee the network requires to process it, it'll get rejected.
T mismatch. Okay, what else?
Time limits.
Huh.
The XDR envelope contains parameters like valid after and valid before. These define a specific window during which the transaction is valid. If it arrives at the network too early or too late outside that window, rejected, expired, or premature.
Right, strict time constraints. Okay, all this transparency we've discussed, seeing the source, destination, the amount in stroops, even those internal memos used for KYC. It really begs a huge question about privacy, doesn't it? Blockchains are famously transparent. How does Pi Network handle user privacy, especially if they want to scale up applications?
That's the inherent tension, right? The transparency is built in. Anyone can see the transaction flows, the amounts held and addresses. Even those muxed accounts only offer relative privacy. They obscure the sub-account, maybe, but the main parent G address is still visible, still traceable on-chain.
So if the blockchain itself is transparent by design, where does any layer of privacy typically come from in the crypto world?
Well, often the main privacy layer gets added externally, usually by the centralized exchanges, the CEXs.
Yeah, they do it.
They tend to batch user transactions together, and critically, they use internal private ledgers that operate off-chain, so they aren't broadcasting every single user deposit or withdrawal onto the public Pi blockchain. They use that memo we discussed to sort the funds internally, which keeps individual user activity somewhat separated from the public view.
Okay, so CEXs provide a degree of off-chain privacy. But what about users who want, real anonymity, much more than an exchange offers?
Yeah, for true deep anonymity, you're looking at more advanced techniques, things you see in the broader crypto space like transaction mixing or routing services, or maybe using specialized exchanges that don't require KYC. But this brings us right back to that core tension specific to Pi Network.
Which is?
Which is that the network seems highly focused on integrating KYC and even KYB, know your business processes.
Wow.
The way they use those internal memos, like the MVP one, it strongly suggests a deliberate effort to track and identify participants, at least at the mainnet beta level.
So that desire for identity tracking, for regulatory compliance perhaps, seems to bump right up against the need for privacy if you want to build, say, advanced decentralized applications on top.
It's the central conflict, I think. How do you maintain the level of traceability and integrity that seems core to the Pi vision, potentially driven by regulatory foresight or their own controls, using tools like unique memos, while also providing the kind of user privacy and maybe even anonymity that many future app developers and their users are likely going to expect or even demand?
That is a really powerful point to consider as the network grows. Okay, let's try and synthesize this. If you, the listener, walk away remembering just 3 things from our deep dive today, what should they be?
Okay, number 1, forget Pi, think Stroops. The true financial unit stored immutably on the chain is the Stroop. 10 million of them make up 1 Pi. That's how the network maintains perfect whole number accounting.
Got it. Stroops are the base truth. Number 2.
Number 2, that memo field. When sending to a centralized exchange, it is absolutely, positively the single most critical piece of data. Get it wrong or forget it, and your funds are likely gone, period.
Memo is life for CEX deposits. Okay? And number 3.
And number 3, how trust is built. Transaction integrity and authenticity, knowing it's real and untampered, are guaranteed because the unique transaction hash is encrypted using the sender's secret private key. The network then verifies that signature using the public key. Private key signs, public key verifies.
Stroops, memo, private key signature.
Excellent.
Now, let's loop back to that tension we just identified for our final provocative thought for you to chew on. We know Pi Network is investing heavily in AI. They have the Pi AI Studio, and they state a goal of massively scaling app creation on their platform.
Right, enabling developers.
Exactly. So given the technical anatomy we've just picked apart, an anatomy that seems to prioritize transparency, traceability through things like specialized memos, and KYC integration, how will Pi Network need to evolve? How might they change their underlying architecture or introduce new privacy features to successfully attract and support those advanced next-gen applications and the users who will operate them? Users who increasingly expect robust anonymity almost as a default setting.
Yeah, it's a fundamental design challenge, isn't it? Pitting that necessary network integrity and potential regulatory compliance against the demands of mass market application development and user expectation. How they navigate that balance, well, the future of the platform might just hinge on it.
A fascinating challenge indeed. We'll leave that thought with you. Until the next deep dive, happy learning.